we are discussing the on-shell renormalization scheme of QED as a preliminary for the standard model. We have discussed the counterterm Lagrangian and the counterterm Feynman rules, and there are precisely three kinds of counterterm Feynman rules, and they affect the three simple 1pi green functions, namely the photon self-energy or the vacuum polarization in simpler terms, the electron self-energy, and the electron-photon three-point function. And that is the formula that we have written down before. There are three renormalization constants: wave function renormalization for the photon, for the electron, and the charge renormalization. And I told you that we must choose a renormalization scheme that is equivalent to defining what are actually the values of those renormalization constants, delta z and delta e over e. There are many different options, and we will now define the on-shell renormalization condition. They are as follows. First, there are on-shell conditions for the fields, conditions which in the end determine the delta z field renormalization constants, and which have to do with derivatives of self-energies. And there are here the two: gamma hat, pi gamma hat of 0 is 0. So this is an equality which is meant as a condition on the renormalized pi gamma, and so it implicitly determines the delta za here. Second, sigma hat at p slash equal to m is also equal to 0. And that is also meant as a condition, and it implicitly fixes some combination of the delta z and delta m appearing in sigma hat. These are two conditions, and they are, I'm sorry about this, I forgot. So this derivative d by dp slash of that at the value p slash equal m is supposed to be 0. And so this equation is a little bit shorthand notation. In principle, it is clear, I hope, what is meant, because ultimately you can express the self-energy in terms of p slash, because it's a 4x4 spinor valued quantity, and so it will depend on p slash, and so you can take p slash as a variable, take derivatives with respect to p slash in a kind of obvious way. But more mathematically speaking, this would correspond to the following. So difference sigma hat of p minus sigma hat, where you set p square equal to m square and have an on-shell momentum, and you divide by p slash minus m in the sense of an inverse matrix. Then you act with this onto a spinor u of p, and then you take the limit where p square goes to m square, so an on-shell limit. Then the denominator becomes singular for p square equal m square. That is not invertible, and so this has a singularity, so that the numerator must go to 0, and this effectively becomes the derivative, and so that should converge for p square to m square to 0. But it is of course simpler to look at the previous equation, and that is sufficient for practical calculations if you know what it means. Then let me continue with on-shell conditions for physical parameters. So there is now sigma hat of p slash equal to m equal 0, and in the same sense this would be equivalent to the relationship that sigma hat of p applied onto a spinor u of p in the limit where p square goes to m square goes to 0. And lambda hat mu of the following momentum assignment. So the photon momentum q is 0, and the electron incoming and outgoing momenta p slash and p prime slash, they are equal to m in the same sense as above, and in that case we set the lambda hat mu to 0. And so that would basically mean that if you have u bar of p prime times lambda hat mu times u of p in the appropriate limit, that would go to 0. Okay. So this box contains the 4 on-shell renormalization conditions for QED, and in the end I have given here the more explicit forms. In the end you should memorize, I think, only the abbreviated forms, and that makes the calculation easy and the physical meaning transparent. Let us now immediately discuss what that means, because it's surely not completely obvious, and let us go through the meaning of all these equations. As I stressed, in the standard model and in QED, the on-shell scheme is essentially perfect. And so that means that all these conditions have very clear, unambiguous, and let's say direct physical meanings. Let us discuss it. So first we need to discuss the behavior of the full propagators, including loop corrections, for the photon and for the electron. So in general, a full propagator looks like this. You have a 3-level propagator, then plus 1 particle irreducible loop corrections, plus 2 1 particle irreducible loop corrections, plus, and so on. And if you sum that, then basically you obtain a geometric series, and what you obtain is a resummation. You can resum all these 1 particle irreducible blobs, and they go into the denominator. And so let me just write down the result for the electron propagator. This becomes I divided by p slash minus m plus sigma hat of p. So the renormalized self-energy, which is this building block here, gets resummed, and it becomes a geometric series. It goes into the denominator like this. And then you see that this self-energy, the 1 particle irreducible blob, has the effect that it changes the denominator of the propagator. At 3 level we have just this, and at the higher order level we have the additional term in the denominator. And that might shift the location of the pole. The location of the pole is the physical rest mass, and it might also change, obviously, other behaviors of the propagator. So what does it now mean if we impose the on-shell conditions? Let us start at the bottom. These bottom conditions are more physical than the ones at the top for the fields. So we have here our on-shell condition for the electron self-energy at p slash equal to m. It vanishes. What does that tell you about the pole structure of the propagator? At 3 level, the pole is at p slash equal m, and therefore the electron mass at 3 level is m. Now, at the loop level, we have this condition. Therefore, the pole is the same. There is again a pole at p slash equal to m that is not modified by the self-energy. That means if the pole is at m exactly, then m is exactly the physical mass of the electron. And that is now not a 3-level statement anymore, but it is an all-order statement by virtue of the on-shell renormalization condition. So the pole is at p slash equal to m exactly. So I will write down in a second that means that the m parameter is the physical mass, but let's first discuss the second consequence. What is the consequence of this on-shell renormalization condition? That the derivative of the self-energy also vanishes on shell. So if we are at the pole p slash is equal to m, then not only is that 0, but also its derivative is 0. What does that mean? It means something about the residue at the pole. The residue at the pole is basically the derivative of the denominator at the pole location. The derivative of this vanishes. Therefore, the derivative of the denominator is the one coming from tree level, is 1. That means the residue at the pole is unchanged compared to tree level. So the residue is 1 in these units, again exactly. So the consequence is that the physical measurable so-called pole mass of the electron is exactly equal to m, where m is the input parameter of our theory, the renormalized mass. Maybe this sounds totally obvious to you and even tautological, but I'm telling you it's not, because in the MS bar renormalization scheme, the m is not equal to the physical mass. Therefore, this is worth stressing. And so the numerical value is 511 and so on keV. I told you that the renormalization scheme fixes the physical interpretation of the parameters and it fixes the numerical value. And in the MS bar scheme, all of this would be different. Next, the residue is 1. What is the meaning of the residue? The residue comes into play in the Lehmann-Symanzik-Zimmermann LSC reduction formalism for S-matrix elements. And there exists this square root of curly z. And this curly z is exactly the residue of the propagator at the pole, which is here 1. This is this wave function renormalization. In the LSZ theorem for S-matrix elements, where the LSZ theorem tells you in complete generality how to compute S-matrix elements at higher orders. And the calculation involves a multiplication with such square root of z factors, where the square root of z comes from the residue of propagators. If the residue of the propagator is 1, then we can forget about multiplying with the square root of z, and we can forget about this step in the LSC theorem. So this is now trivial. So therefore the S matrix gets a simplification. So this statement here is the first consequence of the on-shell renormalization scheme, and it immediately shows you the value of this condition. We have a physical input parameter which is directly connected with an important observable, and we have on top of this a simplification in the computation of the S matrix. Let us go to the photon propagator. The full photon propagator is equal to the following. So let me write down immediately the full result. Minus I g b mu minus q mu q nu divided by q square overall divided by q square times 1 plus pi hat gamma of q square minus I psi q mu q nu divided by q to the 4th. Okay, so let's first forget about the pi. if you remove the pi, then we have the tree-level photon propagator, and it has a transverse part and a longitudinal part, and for psi equal 1, the longitudinal part cancels, and we only have g mu in the numerator. All of this is something you know. And now, because of this resummation here from the geometric series, and from the fact that the self-energy is purely transverse, only the transverse part gets a correction, and the correction involves just this vacuum polarization pi hat gamma from before. And therefore, you see two things. First of all, where is the pole located? At 0, and that cannot be changed because this pi gamma enters in a multiplicative way. So the pole is at q square equals 0, and so there is no free parameter associated with the location of the pole. In other words, there is no free parameter associated with the mass of the photon. Why is there no free parameter associated with the mass of the photon? Because the photon must be massless because of gauge invariance. And why is that not disturbed by loop corrections? Because there are Watt identities and Slavnov-Taylor identities which reflect gauge invariance on the level of loops. And therefore the masslessness of the photon is an all-order statement which is visible here in this equation. And we have exactly written down the corresponding Watt identity, which was the one which led to the introduction of the vacuum polarization pi gamma. The fact that the self-energy is transverse followed from that Watt identity, that gave rise to the appearance of pi gamma, and that is why only the pi gamma appears like this in the denominator, and there is no additive term. Here there is an additive term, but there is no such additive term in the photon case. So our renormalization condition could not do anything connected to the photon mass, but there is something about the residue. What is the residue at the pole? The residue of the pole comes from the derivative of pi gamma at q square equals 0, and or pi gamma at 0, and pi gamma at 0 vanishes because of the on-shell condition. Therefore, the residue is 1. So this is what we have achieved in the on-shell scheme. So massless photon from Watt identity, and this curly ZA, which would appear LZ, is not necessary, would be equal to 1. So again, also for the photon, the calculation of the S matrix doesn't require introducing such a curly ZA from a non-trivial residue of the photon propagator. And that follows from renormalization condition. All right, any questions or comments?
So this means to, for example, that my P cannot be dependent on, for example, 1 over q squared.
Yes, this is exactly something that we already said in other contexts. So these one-particle irreducible Green functions in perturbation theory are regular. They cannot have power-like divergences, like there cannot be a 1 over q square inside of pi gamma. For q square equals 0, there might be logarithms of q square, which are singular, but there are no power-like singularities, at least in perturbation theory. That is clear from the structure of Feynman diagrams. And so therefore we know for sure that there is no shift in the photon mass. You are exactly right. So if pi would contain 1 over q square, then that would correspond to a non-zero photon mass. Yes, but it is clear in perturbation theory that that does not happen. Okay, these are 3 of our 4 on-shell renormalization conditions. So we fix the masses. One mass is actually fixed a priori, the other mass is fixed by the on-shell condition, and the wave functions are both fixed by the on-shell conditions. Now our 4th on-shell renormalization condition for the interaction. That is obviously the most complicated one, so we also need to discuss it. So maybe let's do it here. So we have a 3-point function. Can you actually read this, or is it too small? It's okay. Okay, so 3-point function. So where we say, okay, it's now I have to write really small. So here this effective one particle irreducible green function building block on shell is equal to the 3-level vertex. This is what our renormalization condition tells us. So at on-shell momenta, where everything is on-shell, then all the loop corrections vanish. Therefore, the 3-point function becomes equal to its 3-level approximation. So 3-level becomes exact by definition. What does that mean? If you now do a measurement, suppose this is an observable, you measure it by experiment, you measure the value of this observable, and then you must compare your experimental measurement to theory. In theory, you know all the loop corrections vanish, therefore your exact theory prediction is 3-level, so it's just the coupling constant E. Therefore, what that means is that your measurement directly translates into a measurement of E, of the electric charge. And so E is defined to mean the charge which you directly measure in experiments which work in a momentum configuration where the photon has 0 momentum, and obviously the fermions are on shell. So these are low energy processes where the momenta are all non-relativistic and particles are basically at rest. So this is the classical limit. So therefore we can say E is defined to be the effective charge for processes in the low energy or classical limit. And so the advantage of this is that this is an unambiguous and well measurable definition. And of course the outcome is that we can define this alpha, which is defined as E square over 4 pi, the fine structure constant, and then measuring E is equivalent to measuring the fine structure constant. So you would now say, in order to measure the fine structure constant defined in the on-shell renormalization scheme, we must do a measurement of some electromagnetic process in the classical limit, in the classical realm, and then we identify our measurement with a 3-level theory prediction and extract in this way the alpha. So, and in this way you obtain numerically roughly 1 over 137 with some further digits. So this is the fine structure constant measured in atomic physics and other low energy processes. So therefore again also for the electric charge, like for the electron mass, we have a direct experimental, how do you say, a constructive experimental definition of the electric charge. And the relationship between observables and the charge parameter does not depend on our loop order. It's an exact relationship that you know once and for all. And therefore, let's say, and this is again in contrast to some other schemes, if you would do more precise calculations, higher order calculations and so on, then the value of alpha cannot change. It is fixed once and for all. Therefore, we already know now from experiment the ultimate value of alpha. And that is not the case for alpha s, for example, where the value alpha s depends on your calculations and your loop corrections that you take into account. Okay, so now you see, I hope, why the on-shell renormalization scheme is so good, because it gives a direct connection to observable quantities for all renormalization constants and for the fundamental renormalized parameters which the theory will ultimately depend upon. Now there is even more, and that comes now briefly. So in our step 4, I think it was step 4 of our plan, would be the following. We should now evaluate the renormalization constants. So that is step 4. So how does it work to evaluate the renormalization constants? It means we take this expression for our renormalized green functions, plug them into our renormalization conditions, and make explicit the condition for the renormalization constants. So because the renormalization constants are implicitly defined by the box here, by the renormalization conditions, but let us evaluate it explicitly. For example, if you plug in the value of pi hat and put it into this condition, what is the condition on the renormalization constant that you obtain? You obtain a condition for delta ZA, which is what? Delta ZA must be such that pi hat becomes 0, so delta ZA is equal to minus pi gamma at 0. And then you have a calculational recipe, because that is the one particle irreducible Feynman diagram for the photon self-energy. You calculate it, and then you know delta ZA. Question? Okay. Next. So next condition is this one. Derivative of sigma hat with respect to p slash. So what does it give? It gives the derivative of sigma without hat plus delta z. So from that we obtain delta z is equal to minus d by dp slash of sigma without hat at p slash equal m. Okay. Next, what do we obtain from this condition for the electron mass? Sigma hat at p slash equal m is 0. So if you go up, then you see at p slash equal to m, something nice happens inside of sigma hat, namely what? At p slash equal to m. That simplifies the sigma hat. Such that you obtain which equation for which renormalization constant do you obtain from that?
So the delta z drops out.
Yep.
And you would just have that this I sigma without the hat
Mhm.
equal to this I delta m.
Yep. And so we can solve this and say delta m is equal to sigma without hat at p slash equal m. And the delta z indeed has dropped out. That was the nice simplification. And so you have a direct recipe to calculate the mass counter term. Then the thing with lambda hat, that is obviously most complicated. And in case of lambda hat, we can say that the sum at the top should be 0, and therefore we obtain this combination delta z plus 1/2 delta ZA plus delta E over E must be equal to minus lambda mu without hat at on-shell momenta. And we have to extract the gamma mu part, so the gamma mu coefficient from this, because the delta z combination times gamma mu must be equal to minus lambda hat. And so actually we see that how can this be fulfilled? It can only be fulfilled if indeed the lambda mu for on-shell momenta is indeed proportional to gamma mu. If it is not proportional to gamma mu, then actually there is no way that the renormalization constants cancel the lambda mu. The sum should be mu. The sum should be 0, but the delta z is proportional to gamma mu, so it can only sum to 0 if the lambda mu itself is already proportional to gamma mu. Otherwise, there is no solution for the on-shell condition. Okay, and so let's write this. This is always proportional to gamma mu in this limit. So, but now in this way, we have solved for the renormalization constants, and for each renormalization constant there is now an explicit equation which would allow you to calculate it in practice. So that finishes basically our step 4, which was in some sense the last step of our renormalization program. The rest would be applications. But the rest is not already all applications in QED, because QED as a gauge theory has some special features which we should isolate and discuss before we can finish the discussion. And there is actually one more very important and interesting physics consequence which follows from Ward identities. We have already encountered the masslessness of the photon and the transversality of the photon self-energy, which follows from Ward identities. And now there is something else which follows from Ward identities, which is crucially important for the renormalization of QED. And so let us discuss this. But first, are there any questions to this setup here? Or any surprises in the results, or any interpretation questions? So, I mean, the practical application would be now that you have all these equations for the renormalization constants. You write down Feynman diagrams, then you compute all these delta Z and delta M once and for all. You know their values, and then you can calculate whatever you want, all complicated processes, and you will need those counter-term Feynman rules, and since you know the values, you can calculate in principle everything. Yep.
Just for reassurance, but this changes order by order, right? Because the sigmas also change.
Yes, yes. So here we have now assumed one loop, and that meant, for example, that here there are some things neglected. Products of delta Z and delta M are neglected. So that would be a little bit more complicated. And therefore those equations would change a little bit in their structure, but not much. Essentially, it always boils down to such a structure for the new renormalization constants at each order, and you would get similar formulas also at higher orders. So the equation structure is maybe a little bit more complicated, but essentially the same. And of course, the values of the sigmas and lambdas, they obviously come from higher and higher order diagrams. Yep. Right. Okay, then let me clean the blackboard and let us come to the next topic. charge renormalization and universality. There is a word identity which tells us two things. It tells us a technical simplification on those equations at the top and an extremely important physical insight about QED and the photon. On the physical level, we obtain charge universality. That is the universality of electric charges among all charged particles, electron, muon, tau, quarks, and so on, whatever other particles you might imagine. Here we only have the electron, but if you would enhance QED by other charged fields, then there would be a universality between all the charges of all charged particles. And that is a physical statement which we will discuss. And the technical simplification is that in this equation here, where you see that in order to calculate the charge counter term delta E, you need a 3-point function. A 3-point function which involves the interaction of the photon and the electron. This 3-point function drops out of this equation here. And you can simplify the equation such that delta E does not depend anymore on this 3-point function, but it only depends on much simpler 2-point functions, namely on the photon self-energy. Charge renormalization only depends on the photon self-energy. And so the second item somehow already explains the first one, namely, if you can calculate delta E just by calculating the photon self-energy, then you see the photon self-energy, there is only one photon self-energy. You can have as many charged particles in your theory as you want, but delta E comes only from the single photon self-energy, which contains loops from all charged particles universally. And so then the delta E does not depend anymore whether you have chosen here to renormalize the charge in the photon electron vertex or a photon muon vertex or a photon tau vertex. Ultimately, it depends only on the photon self-energy, whatever you started with. And so therefore, in this sense, the charge is universal. Let us elucidate both statements and let me show you the word identity where it comes from. And let me do it again in quantum field theory 2 notation. For the derivation at least, and then, so for the derivation we use some technical expressions from the other lecture. So we take the Slavnov-Taylor identity, which contains the word identity of QED, and we apply onto it 3 functional derivatives. We apply a functional derivative with respect to a ghost, with respect to psi bar psi for electron incoming and outgoing. And then we set all the fields to 0 after taking the functional derivative. And then there is again some identity between explicit green functions which comes from that. And let me write it down and then we can see how we can understand it. So there is on the one hand a non-zero contribution from this thing where, so in this gamma star gamma, we have external fields coupling to BRST variations. So here there is some BRST source with a BRS transformation of the gauge field, and here there is the gauge field, and then we distribute our 3 derivatives in this way. And then there is a term plus gamma psi bar c k psi bar gamma psi bar, and a third term where psi and psi bar are exchanged psi c k psi psi bar. And what is important is the momentum assignment to all those green functions in momentum space. We have to assign some inflowing or outgoing momenta to these three fields, and then the other fields which are on top of those derivatives, they are defined by momentum conservation. So here, for example, we put the ghost momentum q, then the other thing is minus q. Here we put p comma minus p prime and q, and then you already see that what has emerged here is exactly the one particle irreducible 3-point function that we are dealing with all the time. This is the 1pi green function for a photon, e plus e minus. This is exactly the quantity which we have dealt with charge renormalization, and the one loop contribution to this was our lambda mu. And the renormalized one loop contribution is our lambda hat mu. And this is a prefactor, so we get here an identity which correlates our 3-point function with other stuff. Let's go on. So here our momentum assignment is that here we have minus p prime, q and p, and here then p minus p. And here our momentum assignment is p, q minus p prime, and here then p prime and minus p prime. And then you see here has emerged the one particle irreducible electron self energy, or the one particle irreducible electron 2-point function with momentum p, and here the same 1pi electron 2-point function with momentum p prime. And here there are some prefactors. So what are those prefactors? The prefactors correspond to the BRST transformations of all the fields. And let me just write what they are. Here in QED there are no loop corrections to all those BRST transformations, therefore they are known. That would be different in the standard model or in QCD. So the ghosts do not interact. And therefore the BRST transformations remain equal to tree level. And then we can plug in what are the BRST transformations at tree level. And so for those of you who have seen this in the QFT2 lecture, you've seen this a few times. For the others, I will just quote the result. So as an example, once again, the BRST transformation of the photon field is d mu of the ghost. Then we do here that derivative with respect to k gives exactly that. The next derivative with respect to c gives the derivative only, and in momentum space the derivative becomes minus I times the incoming momentum, so that becomes minus I q mu. That's what it becomes. And similarly for the other prefactors. And so let me not derive this, because it would take knowledge from quantum field theory 2, but quote the result. The result is then this: 0 is equal to minus I q mu times this 3-point function psi bar a mu with momenta p minus p prime and q. This is exactly our desired 3-point function, plus I e q times gamma psi bar p minus p minus I e q gamma psi bar p prime minus p prime. And this is now a nice identity which correlates the 3-point function photon electron electron with the electron self energy and with known prefactors. And let me write it also in a graphical way. So in a graphical way we can bring this term to the other side of the equation and we can cancel the i's, and then we have q mu times the one particle irreducible green function with photon electron positron, and the momenta are always q P prime. So this contraction is on the left-hand side of the equation. And on the right-hand side of the equation, we have E times Q times the difference between two self-energies, namely this electron self-energy with momentum P minus the same with momentum P prime. Okay. This is the identity. So graphically it becomes probably most transparent. On the left-hand side we have an interaction with a photon, contracted with a photon momentum such that the Lorentz index here goes away. And on the right-hand side we have a difference between the corresponding two fermion self-energies, which you get from that diagram by removing the external photon. So it's a relationship between, let's put it in that way, you take some charged particle, and then there are, on the one hand, green functions only involving the charged particle and additional green functions with an additional external photon. And there is this relationship between the green function with the external photon and the ones without the external photon. And that relationship comes from gauge invariance because, as usual, the contraction with the photon momentum is similar to taking the derivative d mu of a current J mu, d mu J mu is 0 because of current conservation, and so such an equation can be interpreted like a replacement or manifestation of current conservation on the level of green functions. So this is what we have done, or what ones without the external photon. And that relationship comes from gauge invariance because, as usual, the contraction with the photon momentum is similar to taking the derivative d mu of a current J mu, d mu J mu is 0 because of current conservation, and so such an equation can be interpreted like a replacement or manifestation of current conservation on the level of green functions. So this is what we have done. Or what we have obtained from the Watt identity, and maybe as a pedagogical check, you can check it at tree level. So what do you obtain at tree level? At tree level, on the left-hand side, what is this at tree level? This 1 pi thing at tree level. So let me know. Or Xavier, you? No. Minus I E Q gamma mu, and then we have E times Q, and on the right hand side, what is the 1 pi electron 2-point function at tree level? At tree level it's just the inverse propagator, the thing coming from the kinetic term of the Lagrangian, so that would be P slash minus M, simply P slash minus M. So then we have here P slash minus M, and on the other hand P prime slash minus M. And then you can check whether it is correct. By the way, we forgot about the I times I, because that is of course I times P slash minus M. And then the mass cancels, and on the right hand side you get P prime minus P is Q, and then it matches. So you see indeed that this equality is really fulfilled at tree level, but we have derived it at all orders, and so it is automatically true also at all orders, and so it is in particular true for the one loop corrections, and in the one loop case it gives a relationship between the one loop corrections here and the one loop corrections there. So at the one loop level we get now Q mu times lambda mu at Q P prime must now be equal to E times Q of sigma of P prime minus sigma of P. So I cancelled a minus 1, therefore here the order is exchanged. Okay. And then you have this relationship between the one loop corrections. one loop 3-point function is connected to a difference of one loop self-energies, and that is also called Watt identity or Watt-Takahashi identity, and that must hold before or after renormalization. Or and it holds before and after renormalization, because the Watt identity is valid before renormalization and it is valid after renormalization. So this is something that holds, and therefore we can use it. We can use it in order to simplify this expression here. Our on-shell renormalization condition makes use of the on-shell value of lambda. Now we know something about lambda. It is connected to self-energies, and therefore this knowledge might be used in order to simplify exactly this equation here in a way which we have announced. Namely, the simplest way to use it, Xavier, how can we now simplify this equation?
To derive both sides by the momentum.
Yes, exactly. So we take the derivative with respect to q nu of this equation and do this at q equals 0. And in our case, we also put p slash and p prime slash equal to m after doing the derivative. So then we have a fully on-shell value of everything, and then we can combine it with our renormalization condition. So if we do that, then in principle at the left-hand side we have a product rule. We get a derivative with respect to q gives on the one hand just the lambda times q times the derivative of lambda. But at q equals 0, and because of regularity, the term with q goes to 0, and then on the left-hand side we only obtain lambda nu. But let's again replace the index by lambda mu at on-shell values. And what happens on the right-hand side? If we take a derivative with respect to q, it's a little bit ambiguous. We must say, because the three momenta are related, let us say p is fixed and p prime is replaced by q plus p. Then a derivative with respect to q is equivalent to a derivative with respect to p prime, but p is a constant. And then this becomes simply a derivative with respect to p prime. That goes to 0, and that becomes its own derivative. So then we have this. By the way, I think, sorry about that. So the lambda had the e times q was factored out of the lambda. Therefore, in this equation, the e times q cancels. So, and then we get here simply this is equal to the derivative with respect to p mu of sigma of p. So now we really have a derivative with respect to p mu, but previously we always had derivatives with respect to p slash. So let's bring that into the picture. The sigma derivative with respect to p slash, and then the inner derivative p slash derivative with respect to p mu gives gamma mu. So and then you see, and that is also at p slash equal m. So that is a corollary of the more general, so that is Watt Takahashi identity, and that is maybe Watt identity also. Okay, so first of all, now you see indeed that from this equation we have now proven that our lambda mu on shell is actually proportional to gamma mu. That is something that I already stressed must be the case, otherwise the renormalization cannot work. And here again the Watt identity guarantees that this automatically comes out. And second, we have now eliminated or at least simplified our lambda mu on shell in terms of a derivative of the self-energy. And so therefore we can plug, it's first of all of course of interest by itself but we can also use it to simplify our renormalization condition. And then we can write this down. So let me not forget to write this. So lambda mu on shell is indeed proportional to gamma mu, and we obtain a simpler solution for charge renormalization. Namely, what is the simpler solution? So if this becomes equal to the derivative of sigma at on-shell values, what happens? We could write here now minus derivative of sigma, but we can also go on and do something more. Namely, at first we have delta z plus 1/2 delta za plus delta E over E is now equal to minus d sigma derivative with respect to p slash at p slash equal m. But we have somehow seen this before, haven't we? Namely, what is that? That is delta z from the field renormalization condition. And so that is now equal to delta z. And what happens if that is equal to delta z?
So the left-hand side of the equation cancels with the y.
Yeah, and the only thing that remains is that this must be 0. And that is then the ultimate charge renormalization evaluation. So we get a much simpler condition. Delta E over E is equal to minus 1/2 delta ZA. As simple as that. So the charge renormalization constant does not require a calculation of 3-point functions. It only requires a calculation of delta ZA, which requires the photon self-energy. So that is equal to 1/2 pi gamma at 0. So only 2-point function required. So that is the technical simplification that I announced. The charge renormalization constant was originally defined via reference to one interaction of the photon with the electron, but because of the Watt identity, that 3-point function drops out of the calculation, and the charge counter term depends only on the photon self-energy. And that is, of course, universal. And so let me now give that physics discussion also in written form. Maybe like this. So some comments on this charge universality. So the fermion type F drops out of delta E. So that means we could have obtained the same result if we would have chosen any other fermion. Electron, muon, tau, etc. Even quarks, one could take even quarks, or in the standard model maybe even the W boson, even though that would require an extra proof. But here in QED that is obvious. And so E means physically several things. what does it mean? We have previously established the interpretation of the on-shell scheme, and E was the effective charge one measures in low energy or classical processes where an electron interacts with a photon. Now we can repeat the same discussion for any other fermion, and the result is the same. Therefore, simultaneously, E also is the effective charge one measures for low energy processes with muons or for low energy processes with taus with any charged particles. So therefore, E and therefore all the effective charges for all those particles, including all loop order corrections, are the same. That is what this means, and that is charge universality. So it means the effective charge for low energy processes with any charged particle interaction with the photon. So like this. And so that means the effective coupling strengths between the photon and any charged particles at in this classical limit are equal up to at most these integer prefactors, the charge quantum numbers q, which you prescribe from the beginning. So up to factor q f, all these effective charges are equal. And so that is a physical statement. It's not only a statement about renormalization constants or unphysical building blocks of the theory, it is really a physical statement about measurable effective charges in low energy processes between different fermions. So it's a very deep and very strong statement which follows here from the Watt identity of QED. So that is nice, and let me now maybe we cover maybe not as much as I wanted to. In principle, I had prepared a few moments of comments on applications. So it's basically obvious what you would need to do in order to apply all of this. We have now constructed the renormalization framework for QED. We have fully understood all the renormalization constants, and we have obtained the most elegant and simplest forms how they can be calculated by loop calculations. So given that somebody would do the loop calculations, we can tabulate all the values of delta E, delta Z, delta M, write it in a table, computer program, and then we can calculate all sorts of processes. And I could just make a few comments on what kind of processes we can then calculate, but it's anyway obvious we can calculate all processes that are of interest for QED, scattering processes like E plus E minus to E plus E minus, Compton scattering processes, E plus photon to E plus photon. We can calculate G minus 2 of the electron or of the muon. We can calculate other corrections, lamp shift, and so on. And one thing that is particularly direct that can be done after doing the renormalization framework is, for example, you can analyze the structure of this interaction between the photon and charged particles. Not exactly in the on-shell limit, because there we know what it is, namely 0, but away from the on-shell limit you can write down form factors such that you get form factors f of q squared times gamma mu plus another form factor times momenta. Okay, And so you can do such an ansatz, and you can prove that this 3-point interaction can be written in terms of 2 form factors, and then you can discuss the physical meaning of those form factors. They come out of the calculation combined with the renormalization procedure that you did. Then, for example, this form factor here is like effectively getting a form factor like the electron becomes not point-like, but it's a charge distribution like the proton or some bound state or hydrogen atom. And this would be the Fourier transformation of the position space form factor charge distribution. So if this is not a delta function, then we have a non-trivial charge distribution coming from loop effects, which are the electron isn't a bound state, but it behaves like an extended charge configuration because of those loop corrections. So this modifies the Coulomb interaction between the photon and the electron. And this magnetic form factor gives rise to G-2 and other effects. So this is now some list of quantities that are of interest and that you can calculate and analyze, and so that is obvious that this should be done if you do physics with QED. And the setup is there and ready for this. But we will not do applications. We will now come to the standard model, but this is just as an outlook for our so-called step 5, which would be now all physics applications that you can imagine. Any questions to QED? Yep.
The last thing that you described is this called the screening effect?
You can interpret it as a screening, so because of virtual E plus E minus pairs in the vacuum, the electron is surrounded, the bare electron is surrounded by E plus E minus pairs and so on, and the photon couples not only to the point-like electron in the middle, but also to all those virtual particle pairs that appear in the vacuum, and the effect of this can be calculated and summarized in this form factor here, yes. That would be the interpretation. Okay, and so of course this was our prelude in QED, and all the things that I have stressed will be repeated for the standard model. So there is nothing here that will not be repeated for the standard model. So charge universality, renormalization prescriptions for the delta Z, Watt identities, and renormalization transformation. So everything that we have said now for QED will repeat itself also for the standard model, just in a little bit more complicated form. In particular, the Watt identities are way more complicated, and the rest is a little bit more complicated. And we have much more things to write down, and therefore it's also an organizational question. Okay, but that is the outlook. Let me clean, and then we can begin. Let me say for the record, also on video and also for you, that there is in principle one thing that one should still discuss in QED, which is also important for the interpretation, but we will not discuss it now, maybe later, which is Thiering's theorem, which is the statement that actually not only the 3-point function vanishes on shell, but also loop corrections to such a process like Compton scattering. They also vanish on shell, and that really means that if you measure Compton scattering in the classical limit, which is then called Thomson scattering, so really a classical electromagnetic process, then you can interpret the result directly in terms of QED predictions. If you calculate the 3-level QED prediction, it is by construction exact. And you can measure it and then determine the QED parameters from this. So this is an extra theorem which one can also prove, and which means that also in more complicated processes the loop corrections vanish. And that also has a counterpart in the standard model. But let's postpone that discussion to a later stage.
So this means if I would have like more family of fermions, for example, would I have a different charge? Because of in the I will have more terms in the photon self-energy.
So the photon self-energy will be different, and so therefore indeed the renormalization constant will be different. But that statement is that the effective charges between the different fermions, they are the same, and that remains true. So the fact that the muon has the identical charge and it couples with exactly the same strength to the photon as the electron, that is a physical statement and that is true. And the value of delta E, however, becomes different if you include electron, muon, tau, and so on. And so, for example, okay, but that is a physics application. We wanted to go to this anyway. So the physics application is, of course, that all processes which are affected by the photon self-energy, and in the end this also plays a role inside of this FV. So they are affected by what fermions and what charged particles can appear in the vacuum. So if you imagine this really like you have here a point like a bare electron, and then it is surrounded by E plus, E minus pairs in the vacuum, and so on, and the photon from far away in the classical limit. Classical limit means the photon has very long wavelengths, so this is now our photon. Then it sees here the E plus, E minus pairs, but it might also see mu plus, mu minus pairs. It might also see tau, tau pairs, and so on. It might see all of that, and so therefore if you have more such charged particles in the theory, and therefore in quantum fluctuations, then the screening effect is different. And that means the value of delta E is also different depending on what charged particles exist in our theory. But the universality statement stays. And as you know, in QCD, if you repeat the same situation for QCD, let's say this would be a quark, then the QCD color charge would not only be screened by color charged fermions, but also it is screened by color charged gluons because of the gluon self interactions, and they have an anti-screening, and therefore you get asymptotic freedom. And at low energies the QCD effective charges become stronger, but at small distances and high energies the QCD effective charges become weaker because of that anti-screening. Okay. But this is all application, and that is of course very interesting, but let us continue with our chapter on renormalization. The electroweak standard model renormalization transformation and counter terms. That basically corresponds to our step 1 and 2 in our general program. And now let me do a simplification. So we will discuss here only the case with one generation of fermions, and so there is no CKM matrix. Therefore, we do not have the task of also renormalizing the CKM matrix, which would be additional work. And like for QED, we assume dimensional regularization, and we assume the validity of all relevant Slavnov-Taylor identity. And then we know what is the correct counter-term structure in principle, namely it can be obtained from the usual field and parameter renormalization transformation, and our job is to work it out in detail and figure out a useful renormalization scheme. Here, let me start with an overview. So first of all, there is a similarity to QED. By the way, there is essentially no similarity to QCD, and I think in this lecture you have already discussed the renormalization of QCD, which is really not analogous to the renormalization of QED and not analogous to the renormalization of the electroweak standard model, because there we can only usefully use the MS bar scheme, but there is no useful on-shell scheme. But here there is, and so there are physical parameters. The electron charge MW, Z, Higgs, and the fermion masses. And all these parameters, which are the ones that we had at the end after our reparametrization, they have, of course, at tree level a very nice interpretation, clearly masses or electric charge, and this is the electric charge of the photon, which should have the same interpretation as in QED. And so therefore, the structure of the parameters which appear are really of the same nature as in QED. So we have masses where an on-shell renormalization makes sense. And we have the QED charge E, and there we can hope to do analogous renormalization as in QED. So therefore, clearly an on-shell renormalization with direct physical interpretation seems promising. So, and indeed it works, and that is the point of this section. So we will see how it works. But before we go to the details, let me point out some options, and then we do the details next week. But there are actually two different approaches done in the literature. So that is one of the first details that I want to discuss here briefly. So there is a setup 1 in the literature, which is the setup by this paper Böhm, Hollig, Spiessberger. From 86. They start from the original parameters and fields. So the fields in particular B mu, W, A mu, and the Higgs doublet phi, and the parameters gauge couplings and Higgs potential parameters. This is what they begin. Then they renormalize them. Then they obtain from this a counter-term Lagrangian, which depends on those fields, the original fields, and on things like delta GW, delta GY, and so on. And only then they introduce the physical fields as we have done at tree level. So then they introduce photon Z, W plus minus, Higgs field, and so on, and the parameters E, MW, Z, Higgs, and so on. Okay. So this is one way to set it up. And what is an immediate advantage of this procedure? The immediate advantage of that procedure, so plus stands for advantage. An advantage is that we know from the general Slavnov-Taylor identity discussions that this is guaranteed to provide exactly the correct form of the counter terms which cancel all divergences and which are compatible with the Slavnov-Taylor identity at higher orders, because that is exactly the outcome. So we did that in the other lecture in quantum field theory 2. So there exists a Slavnov-Taylor identity which governs the possible divergences, and you can evaluate the structure of all possible divergences, and you figure out that it corresponds to a renormalization transformation of the original fields, gauge couplings, gauge fields, and so on in your Lagrangian. Therefore, this is guaranteed to be in agreement with that general statement. Therefore, whatever counter terms come out of that procedure are guaranteed to be sufficient in order to make the theory finite, and they are at the same time guaranteed to not interfere with the validity of the Slavnov-Taylor identity, which is of course also important. So that is the key advantage. So symmetry. All divergences, at least all ultraviolet divergences, cancel, and Slavnov-Taylor identity is preserved. There is a second advantage, which is simply minimality. So it is at the same time the minimal number of renormalization constants that you can introduce, and you will see in the next approach this is not minimal. The drawback, however, is that in this approach you have not enough freedom to choose renormalization schemes which you might like to choose, namely you have not enough freedom for full on-shell conditions for all fields. So one will encounter that some fields, for example the neutrino fields or maybe the Z boson field, in the end you cannot have residue equal 1 of the propagators, and then you have some of these curly Z factors which are not trivial, necessary for the LSC theorem. Okay, so however, this is one approach, and now let me contrast this with the other approach, which is by the other two kinds of papers I mentioned in the morning. So setup 2 is by Denner et al. And also by Aoki et al. And this is the opposite. We immediately start from the Lagrangian that we have derived or sketched in the morning, which is parametrized in terms of the physical fields, photon ZW, electron charge MW Z Higgs, and so on. We take that Lagrangian and apply onto it a renormalization transformation. So start from there and renormalize. And the advantage is obviously now that we can fulfill full on-shell conditions. And all these square root of curly Z factors are equal to 1. That is the key advantage of that setup. And let me just briefly mention a relationship between the two. For example, for the photon and Z, this relationship is kind of important because it establishes, since the first one is guaranteed to be in agreement with all the symmetries, if you can relate the two, then also the second is in agreement with the symmetries. So that is the importance of that relationship. And let me just illustrate it. So in the first approach, you would simply have in the Lagrangian, for example, the B field and the W3 field in a Baire form, and they would be related by square root of Z vectors, ZB, ZW, to the renormalized B and W3. And that is then the correct structure to cancel all the divergences. And then later that is replaced by photon and Z in the way we did it in the lecture. But now you can do, so that would be a set of 1. But now you can say that this is equal by definition to what we have done in the lecture, but promoted to a Baire form, so that we would have cosine minus sine, sine, cosine Baire times the Baire photon and the Baire C field, and you can simply replace that object in the Lagrangian by this, and since it is set equal, there is no change, and if this is the correct form of the Lagrangian, then after that replacement it is still correct. Then you have a Baire Lagrangian expressed in terms of a Baire photon field and a Baire Z field. But on the other hand, at the end you can replace this here, B and W3, by a general matrix R times photon and Z, where this is a general finite 2 by 2 matrix. And so why is it finite? Because at this point, after you have introduced those renormalization constants, they were already sufficient to make the theory finite. That is what was guaranteed by the Slavnov-Taylor identity. So expressed in terms of those renormalized fields, the theory is finite. And then you can simply, in a finite theory, redefine your fields in any way you want. Nobody can stop you from defining completely new fields called photon and Z, which are simply some linear combination of the previous fields. And that doesn't even have to be an orthogonal linear combination. It can be any linear combination you want. Nobody can stop you from doing that. And then that means, since the theory was already finite at this point, it is also finite at that point, and so you can express a finite theory in terms of finite photon and Z boson fields, which you have introduced in this way. And the combination of all these equations means that in setup 2, what you effectively do compared to setup 1 is that you have a Baire photon and a Baire Z boson field, and they are related in the following way. So you have cosine Baire, sine Baire, minus sine Baire, cosine Baire, we make mixing angle, then square root of ZB, 0, 0, square root of ZW, and then a finite matrix R times renormalized photon and Z fields. And then you can express on the one hand your Baire Lagrangian in terms of Baire photon and Z field, which is then by construction exactly our tree-level Lagrangian, just written with Baire quantities. And you can apply this complicated looking renormalization transformation and obtain a Lagrangian in terms of renormalized fields and renormalization constants. And you know that the resulting theory is first of all finite and symmetric, but contains general photon and Z boson fields, which are some arbitrary linear combinations of other fields that you have, you are able to choose. And so here, what appears here is simply a general 2 by 2 matrix with divergences, and so you can call this a square root of Z matrix, where Z is equal to unit matrix plus delta Z is a general 2x2 matrix. In particular, this is neither unitary nor Hermitian nor symmetric nor something else. The delta Z simply has 4 independent components which can be chosen in order to fulfill some renormalization conditions. And the comparison with the previous setup shows you something, and that is a little bit why I'm highlighting this. It shows you that the 4 different components of the delta Z matrix, they are actually functions of 3 divergent quantities. Therefore, there is one relationship between the 4 entries. So not all the 4 divergences are independent. Here there is a divergent counter term for the weak mixing angle, and here there is 2 Z factors for the fundamental fields of the theory. So these are 3 potentially divergent renormalization constants, and out of those 3, together with this finite matrix, we construct a general 2x2 counter term matrix. And so in principle you would be able to derive some relationships between the 4 entries which would be finite. And one could check that in a practical calculation, but what is more important than this is that we see that it is correct to simply say I start with a Lagrangian expressed in terms of bare photon and Z, apply a completely general matrix valued field renormalization transformation, and then obtain a correctly renormalized counter term Lagrangian. And that is what we will do. So we will follow this setup 2, this Denner approach, where we can fulfill complete on-shell renormalization conditions, because there the physics interpretation is even more direct than in the setup 1. And so that is really maybe the ultimate on-shell scheme, which is then also the, I would say, role model for the renormalization of any other theory if you want to apply the on-shell renormalization scheme. Okay, and how that is done we will do next week. Okay, so see you then.